Okay, so that first whole part of the lesson is just basically just rewriting points in a new way. That's all it is. But if we can rewrite points in a new way, we can rewrite equations in a new way. So bear with me for a couple minutes while we convert equations from one style into another. So this would be considered converting equations from rectangular to polar. Form. And the examples I'm using are just kind of like the ones from the book, because they do good examples. You basically, whenever you teach this, you just kind of teach it from the ground up. So I'm going to start with the simplest case I can think of. What's the simplest equation I've ever graphed in this class? Y equals what? Y equals x. I would agree. That's one of the simplest graphs we have. It's super simple. So I guess the question is this. What would happen if we changed x to r cosine theta and we changed y to r sine theta? Let's try it. If I change this to r sine theta and this to r cosine theta, what happens? Well, the tradition here is to solve for r, if possible. Normally you try to isolate r now. I don't think that's going to be real easy to do. Why don't we at least bring all the r terms to one side? So we'll just subtract everything over to one side. And maybe pull out an r. Okay, I have basically a product equaling 0. So I'm going to interpret this to mean that either r is 0 or sine theta minus cosine theta is 0. One of these two statements is true, or maybe both of them. Right. The first one's not very interesting to look at. It's just r equals 0. It's kind of a trivial little statement. But look at the second one. Can you think of an angle where sine and cosine give the same number, so when you subtract them it would... Okay, yeah, didn't let me finish my sentence, but that's okay. Basically this is saying that sine is cosine, see? You could even divide both sides by cosine and write tan is 1. You could divide both sides by cosine, see? And you guys shouted out some possible angles here. You said 45 degrees, right? What's another angle where sine and cosine are the same? 225, right. Okay, so I'll go ahead and write both of these. So I kind of came up with more than one answer here. I came up with r equals 0, and I came up with theta equals 45, and I came up with theta equals 225. Let's take a look at what these all mean. So let's say I told you, you must draw r equals 0. Ready, go. What would you draw? If I said draw r equals 0, ready, go. What is that? You're supposed to draw all the points where the distance to the pole is 0.
That's just the pole.
That's just the pole, right. So the first graph is that of r equals 0. Not a very interesting graph. Just basically a point located 0 units from the pole, or the origin. Okay, now this next one in red means something else. It means you must find all the points where theta is 45. Well, there's a lot of those. You never told me what radius to use, so I could draw any of these points. Theta is 45 for any one of them. Every single one of them has theta equals 45. And theta equals 225 is down in the quadrant 3 here. But honestly, if I allow r to be negative, if I allow backwards motion, 45 is good enough. Because I'm going to get these anyway if I walk backwards away from 45. So what graph did I just create? The y equals x line. See? It's the same line. It's still y equals x. It's just from a slightly different perspective. We're thinking of it as more of a 45-degree line instead of a slope 1 line. But slope 1 and 45 degrees means the same thing anyway. Okay, so here's my conclusion. Y equals x is the rectangular form And r equals 0, theta equals 45, this two-part answer is the polar form. Now, if somebody told me to draw all the points where where theta is 45, I technically might not have drawn this black dot because that point doesn't have any angle. You see? It's like if you're standing, right, at the pole, and someone says, "What's your angle?" You'd say, "I don't really know. I guess it's just which way I'm facing." If you're standing at the pole, which way you're facing might be the angle, but you haven't actually gone or done anything, so we don't really count this point as having an angle associated with it. That's why we got two answers. This fills in the little hole right there, and this is all the other red points. Positive R's and negative R's. In any case, these two together do form that line, don't they? So from now on, for sake of convention, we're going to allow R to be 0, even if an angle is given. So we're going to actually just finally settle on this. And we won't write the R equals 0 anymore. Again, the reason is, even though R equals 0 has no angle associated with it, we allow you to pick any radius you wish with this angle. So it would include the origin if you decide to make R 0. Okay, let's try a different one, something a little more complicated. So what's sort of the next equation that you learn to graph? We graphed y equals x. Evidently, the equation for that is theta equals 45 in the polar world. What's the next graph you learn to graph? Y equals x squared, probably, right? Okay, let's play the same game with y equals x squared. We're going to change this to r sine theta, and we're going to change x to r cosine theta. In other words, we get r sine theta equals r squared cos squared theta. And our efforts to solve for r, that's usually what we try to do. Let's bring everything to one side. And let's factor out an r. Okay, so we get two solutions. R equals 0, which means we'll be plotting the pole. And watch close. Here's the other equation right here. Don't miss this. Set this equal to 0 and solve. That timer is for anyone taking the quiz. Okay. So this gives me basically r cosine equals sine, and let's divide both sides by cosine. So r equals tan. R equals tan.
What happened to the cosine squared?
What happened to my square on the cosines? I have no idea. You're right. This is a cosine squared, not a cosine, isn't it? So it's actually tangent secant. When you divide sine by cos squared, it's like dividing by cosine twice. So you get a tan from these two and a secant from that one. Okay, so you're right, it's tan sec. Now, I would much rather graph y equals x squared than graph r equals tan sec. I just think r equals tan sec is kind of confusing. But honestly, they're exactly the same thing. So let's write our conclusion at the bottom of the page. Y equals x squared is the rectangular form of a parabola at 0, 0, vertex at 0, 0, right? And r equals tan theta sec theta is the polar form of a parabola with vertex at 0, 0. Interesting. Okay, Okay, now before you decide that the equation in polar world is always uglier than the equation in the Cartesian or rectangular world, I think I can change your mind about that. Let's go on and try a third example. Do you guys remember graphing circles in Algebra 2? Okay. Let's go to the next page here. Let's say that I had you convert x squared plus y squared equals 25 to polar form. That's a fairly ugly equation, but it's a circle with radius 5, and it's centered at 0, 0. That's, in fact, we can graph it. It's really simple. Just basically looks like this. Okay? But watch what happens when you convert it into the polar world. You put in an r cosine for each x. You put in an r sine for each y. You're not going to touch the 25. You get r squared cos squared plus r squared sine squared equals 25. And in your efforts to solve for r, you might want to factor. But what's cosine squared plus sine squared? 1, right. So you just end up with this. In other words, r equals 5. So in the world of rectangular coordinates, the circle has a fairly ugly equation. This is rectangular form of a circle. But look at the polar form of a circle. It's so simple. R equals 5. Now, let's say that you were asked to graph. Let's say that this was back in Algebra 2 days, okay? And let's say your teacher told you, please graph on your graph paper x squared plus y squared equals 25. This might take you a while. You might plug in like 5 for x, and you might try plugging in like 3 for x, and you try to figure out what y is, and you plot for like a half an hour, and you realize, oh my goodness, this is just like a circle with radius 5. So that took you forever, right? But if you had first converted it to polar form, it would have been so simple. You would have just said, oh, I need to find all the points where the distance to the pole is 5. That's this one, and this one, and this one, and this one, and this one. See? So the polar representation is so much simpler. And this is why we have two systems. Because sometimes the equation in the polar world is actually simpler than the equation in the rectangular world. They mean the same thing, but look how simple this is. You see? Now what would happen if we shifted our circle a little bit? You know what I mean? Like if it were not at the center, like 0, 0. Let's see what happened there. So let's play around with this for a minute. Make the changes for me, okay? You're going to change x to r cosine, you're going to change y to r sine, and you're going to use this equation. Take a moment and just switch your x to r cosine theta, switch your y to r sine theta, and then FOIL the whole thing out. See if you can get the r by itself, okay? This is called converting an equation. Give it a try. Grades don't mean much right now anyway. Okay guys, so let's take a look at how this all expands out. So you're going to get an r squared cosine squared. That's from squaring the r cos. You're also going to get a minus 10 r cos. That's your cross term from a minus b squared. You get a minus 2ab there. And there's a plus 25 chilling here. And there's a plus r squared sine squared. And there's a 25 on the other side, see? So it looks like some things actually kind of combine or cancel. And you can see that this cancels with this. That's nice. And then this term and this term are so similar. Let's at least put them together. So we have r squared. Why don't we factor out an r squared from that first and fourth term? What are we going to do with this minus 10r squared? I'll probably just put it on the other side in just a minute. I meant 10r cos. Okay, so this is sort of everything rewritten. I put the underlined terms together. I left the minus 10r cos right there. The 25's gone. 0 on the right. But what's cosine squared plus sine squared? 1, right. So this is just r squared minus 10r cos equals 0. And if I factor out an r, I can get that. Which leads me to two things. One, a graph of the pole. This happens quite often. That's just a plot of the origin alone. Not very interesting. But the other one's more important. What does this tell us? R equals what? 10 cos theta. Okay, so interesting. A circle has, if you look back at the previous example, the equation of a circle in the polar world is sometimes r equals 5. That's when it's centered at the origin. But sometimes, if things are a little shifted around, it might be something a little bit different, like 10 cosine theta or something. All right, so now I'm going to show you real quick that your calculator can actually graph this as written. So everybody turn on your calculator and go to mode, and you'll notice there's some things in here we've never looked at before. Like at the top line there is how you want your calculator to do the rounding, and the second line as well. Then there's radians versus degrees, but what's this? Func, par, pol, sec, what is that stuff? We're going to choose polar, P-O-L, polar.
Where is that on the cherry?
Press, for you, you press mode, and I believe it'll say function.
Yeah.
Push your right arrow and go down to choose polar.
Okay.
Okay, watch this. Press the y equals button that we normally press when we're going to graph something, right here. It no longer says y1 equals.
R1.
It says r1 equals. Also, at this point in time, let's put this calculator in radians. Very important. So you definitely want your calculator in radian mode, as mine is. Okay? So press mode, and make sure it's in radian mode. So I pressed y equals, and now it says r equals, and you're supposed to treat your theta as if that's sort of like your x now. So you're going to be graphing 10 cos, and the old x button now no longer types x, it now types theta. See? So you can type this equation as it's written, just go to here and type 10 cos x, and it now looks like 10 cos theta. Okay, now this is really cool. So what the calculator is going to do is, and I want to show you the table first and then the graph. What the calculator is going to do is, if you press table, it's going to pick random values of theta, just like in the past you would pick random x's, right? So it's going to pick just a bunch of random thetas. It might pick 1 radian, 2 radians, 3 radians, 5 radians, and it will plug them in, and it will get an r value. Okay? So what the calculator is doing is it's just plugging in thetas and getting r's as a result. So the first point here says 0, 10. What does that mean? That means if you decide to go with 0 degrees, right? 0 degrees, which is over here, 0 radians, you will be 10 spaces away from the pole. So out here at theta equals 0, you are at 10 spaces from the pole. And then the calculator decides to try 1 radian. 1 radian, that's about 57 degrees. And the calculator learned that r is going to be 5.4, see? So if you go up here to like 1 radian, that's about in here, it's only 5 units from the pole. See? And when you're at 2 radians, that's about 120 degrees-ish, it's at -4. So you would basically go out here to 120-ish, but it's walking backwards 4. And what's happening is it's plotting points. And it's going to form a circle shifted to the right 5, which is the equation we gave you, by the way. A circle shifted to the right 5. And now let's take a peek and see how the calculator actually graphs it entirely. So just press graph. You'll have to probably do a zoom standard if you haven't done that in a while. There's your circle. Okay? Now it looks more like an oval. That's just because we need to do a zoom square. So if you choose zoom and you go down here to option 5, it'll make it where the x and y axes are more one-to-one scale. And now you can see it's a nice, perfect circle shifted to the right 5. Radius is 5. Okay? So this is just introduction to the idea of graphing polar curves and how to convert. We'll do a lot of graphing in A3, or A2 I mean, and I'll give you some polar graph paper. It'll be fun.